Hey guys, afternoon. I'm sorry, I need just one more second, okay? I'll be right back. I know we're running a little bit late today. I appreciate your patience. Okay, sorry about that, guys. Switched over to the doc cam and we can get started. So this is Calc 1. Today is the 31st. And today we're going to start talking about limits a little bit more formally. We'll start dealing with them algebraically. So today we're going to go a little bit deeper into chapter 2. Specifically, we're going to talk about sections 2.3 and maybe a little bit of 2.4 if we have time. So 2.3, we're going to learn some laws for limits, some rules for how limits operate as algebraic structures. 2.4 is not a section that we're going to cover in detail, but I wouldn't mind talking about it just a little bit. So today we're going to look at 2.3, which is on limit laws. And maybe a little bit of 2.4. And then later in the week, we're going to connect that to continuity in the way that I've kind of been hinting at, and then we'll start studying continuity as a rigorous algebraic thing. So before we get into this, I just want to say if anybody needs more time on any of the WebAssign work from last week, you can always submit an extension request. There's a little link right there in the WebAssign homework window where you can request an extension, and I'll always grant those. Generally, I'll just grant them. I'll push things back 1 week. So if you need more time to finish homework 1, that is an option for you, and you should go ahead and submit that request today as soon as you can, because I like to go through and clear those before opening the next week's homework. So we've seen how you can take limits of functions if you know the graphs. So for what I'm about to write, go ahead and assume that you have the graphs of f and g, and that you can calculate those limits just by looking at the graph. And we'll talk about how to break it down algebraically using these laws under that assumption. So if this is a theorem, and these are called the limit laws. And this will allow you to take hard limit problems and break them down into simpler limit problems. That's the basic idea. So if the limit as x approaches c of f of x and the limit as x approaches c of g of x both exist, then the limit as x approaches c of f of x plus g of x, you have a limit of a sum of two functions, then you can split that up and take the limit of each on their own and then add them to each other. So that's the limit as x approaches c of f plus the limit as x approaches c of g. And there's nothing sacred about this plus symbol in between there. If that plus were a minus, then this plus would be a minus, and that works just fine. Also, if you have a limit as x approaches c of a product, f of x times g of x, then that can be treated as the product of the limits. So you can take the limit of f and multiply it by the limit of g. So maybe it's hard to see, maybe you don't know what the graph of f times g looks like, so you can't tell what that limit would look like on its own as it is, but you do know what the graph of f looks like, you do know what the graph of g looks like, so you could calculate each of those limits on their own. And this rule tells you, though, that the limit of the product is the product of the limit. So you can just take each of those limits that you could calculate on their own and multiply them, and that would work just fine. If it works for sums and differences, and it works for products, then it works for quotients also probably, and that's true under one additional stipulation. So if you want to take the limit of the ratio f of x over g of x, and again, maybe you don't know what the graph of f over g looks like, but you know what the graph of f looks like, and you know what the graph of g looks like, so you could take the limits of each on their own, then that's just fine. You can take the limit as x approaches c of f of x, and divide that by the limit as x approaches c of g of x. But this has one additional stipulation, and that's that the object downstairs, the limit as x approaches c of g of x, is non-zero. So of course we can't divide by 0. Okay, so these are the basic.
Then again, what if the top one is 0 too? So.
Well, 0 over 0 would be an indeterminate form. So if that were the case, that both the top and the bottom were going to 0, then this step wouldn't really help us, would it? In fact, more often you'll go the other way. More often you'll have a ratio like this, where you're thinking of the limit of the top over the limit of the bottom, and you're like, oh shit, those both come out to 0. And then you'll try to combine these and factor or cancel something algebraically so that you can get it out. But here we're thinking of moving in the one direction from left to right. So if you were trying to take a limit like this and you didn't know what this graph looks like, but you do know what this graph looked like and this graph look like, then this says it's okay to take the limit of the top and bottom separately as long as the bottom isn't 0. If the bottom is 0, then splitting like this isn't advantageous. That's the idea there.
And just to clarify, you're saying as x goes to c?
Mm-hmm.
Okay.
Yeah, all of these are as x goes to c, where c is just some real number, right? Could be anything. There are a few more that I think the book drops on you at this stage. Or we go back here. You can take limits of powers, and those play nice with the power operation. Let's see what other ones they give you at this point. Yeah, they split those up, right? Okay, so these are the basic ones that they give us. Oh, and the constant. Yeah, sure, okay. So if you have some constant k, they misuse things here and use the same symbol in 2 places. But if you have a limit of a constant times a function, and you know what the limit of the function is, you can pop the constant outside the limit. So the first item, together with the fourth item, is what would tell us that the limit operator is what's called a linear operator. It splits up nicely over addition, and it splits up nicely over constant multiplication. The guys inside here, they don't have a special name, but they, it's just that limits can be split up over multiplication and split up over division as well. Separate from this theorem, the book goes on to list several other things that I'm going to list as a part of this theorem. And we'll come back and look at some of those examples again, but each of these is also important. So the fifth thing that they list here is that the limit of a constant function, so the limit as x goes to c of a constant function, is just that constant. And then the limit of a power you can shove the limit inside the power. Like so. And this actually, this guy right here encapsulates the rules for roots as well, if you think about it, because even though your book lists it as a separate thing, an nth root is the same as the 1 over nth power. And this works great regardless of whether the power is an integer or not, as long as everything plays nice. Let's see. Yeah, I guess, so what they're doing here is giving specific cases that we can use. So we'll go ahead and list them as well. So some common limits. I'm not going to treat these as though they're a part of that theorem because they're not, but some common limits that we use all the time. That the limit as x approaches c of x to the n is just c to the n. Let's see, and again, you could take this as being a special case, but you could say the limit as x approaches c of the nth root of x, that will be the nth root of c. So these aren't limit laws. We're not breaking up a limit or anything. We're just saying that the function, any sort of power function, if you're trying to take the limit as x approaches c, you'll just get c to the n. There's one exception here, provided c is not 0 when n is less than 0. So if this was like 1 over x and you're trying to send x to 0, then of course this doesn't work. And the same deal here, you need provided c is positive when n equals an even number. Because of course you can't take an even root of a negative number, at least not without getting complex numbers, and if we were to start working with complex numbers, then calculus actually becomes considerably harder to work with. Okay, yeah, so I can flip back over, we can get some things copied. There's a question in chat about where to find the YouTube videos. They're in the same announcement where you find the Zoom link. So the YouTube link for each video will be found in the same announcement where you find the Zoom link for that day's class. You can also go to my YouTube channel, and I'm sorting these into a playlist. So you go to the playlist for MAC2311.004, and you'll find all those videos there in order. So these are our limit laws. And these are some common limits that we use often. I don't think this one is in your book, but I would go as far as to say here that the limit as x approaches c of an exponential function can always just be calculated by plugging in also. That's essentially what we're saying with each of these common limits. That you can calculate the limits of these nice functions just by plugging the value c in for x, as long as everything is happy domain-wise, right? So as long as you're not taking an even root of a negative number or trying to raise 0 to a negative power, you can just plug in. So these, together with that theorem on common limits, are enough for us to start crunching out quite a lot. But before we get into that, there are some kind of abstract examples that we want to go through to make sure we understand the rules. So assume that the limit as x approaches c of f of x is equal to 2, and the limit as x approaches c of g of x is equal to 1/3. Can we find the limit as x approaches c of 3g of x minus f of x? How would we go about doing this guy? And while
I
you
had a question.
Sure. Yeah,
So each class is different. theorems, is this something that we should memorize or have in our head for tests and whatnot?
So yeah, you raise a good point. Different professors have different standards for how well you need to know the theorems. I would say, I don't think it's necessary to, for example, make like flashcards of all the theorems and memorize the hypotheses and the conclusions. What you should do is work lots and lots of problems. Work with the exercises that depend on those theorems until you're comfortable enough making use of them, because this is more a skill building class than it is like a proof-based class. As long as you're comfortable with how the theorems are used to get the results, you'll be okay. Calc 2 gets a little bit more rigorous. There will be places in Calc 2 where you're expected to state and understand theorems in their entirety, their hypotheses and conclusions. In this class, that's not so much the case, with a few exceptions. So when we get to a theorem where I need you to know the theorem precisely, you know, all the stuff that comes before the if, and then all the stuff that comes after the then, word for word, so that you can check if that theorem applies to a given situation, I will let you know. So this is not a theorem like that, but this is a theorem that you'll get comfortable with through use. And all I require here is comfort, not like rigorous mastery. Does that answer the question? You feel comfortable?
Yes, thank you.
Okay, cool. So the attack for part A here, we would want to use our limit laws to split this up. So I could treat this as the limit as x goes to c of 3g of x minus the limit as x goes to c of f of x. That's using the rule that says the limit of a difference is the difference of the limit. So you can split up the limit over subtraction. And then if you wanted to be very careful about it, you can pop this 3 out, because the limit of a constant times a function is the constant times the limit of the function. And this guy we can leave alone. And then from here, we do know everything. So the limit as x approaches c of g of x, oh, I was told that that's 1/3. So I'll finish this line over here. This will be 3 times 1/3 minus the limit as x goes to c of f of x. Oh, well, that's 2. And the 3 times 1/3, that's 1. 1 minus 2, that's -1. So this first guy is -1. Good, yeah, and the second one will follow similarly. I'm going to give myself a little bit of space, so I'll come down here. I would say that I can split this up over the division. So this is the limit as x approaches c of the numerator, which is 2 times f of x, divided by the limit as x approaches c of g of x. And then upstairs here, I can pop out the 2. So this will be 2 times the limit as x approaches c of f of x, divided by, this is just the limit of g of x now, the limit as x approaches c of g of x. The numerator is 2 times, the limit as x approaches c of f of x. Oh, that's 2. So the numerator is 2 times 2. And the denominator here is 1/3. And we need to be careful with our fraction arithmetic. That's 4 times the reciprocal of 1/3 is 3. So this guy would be 12. So nothing too mind-bending here. The core idea of the start of this section is that if you're given a limit that looks a little bit complicated, try breaking it down into its pieces, because the limit operator plays nice with every form of arithmetic. So division, addition, subtraction, powers, all of it. You can break up your limit over all those things and try to ask yourself, which pieces can I recognize? Any questions on these examples? Okay, cool. So let's look for something a little bit tougher. I suppose we should do something like that. So here, I'll grab a similar example. If you want to take the limit of a polynomial, for example, you wanted to take the limit as x approaches 2 of the polynomial 3x cubed minus 4x squared plus 2x minus 1. Certainly you wouldn't always want to do it this way, but you can use the limit laws that we've discussed to split this up, because for sure I have no idea what the graph of this big gnarly cubic polynomial looks like. I can't say I'm going to look at the graph of this function and imagine sending x close to 2, because I don't know what the hell this graph looks like. And we don't want to be dependent on graphing hardware. We don't want to be dependent on graphing software. We want to be able to do these things by hand. So I would split this up, and I'm going to do these steps together now as 3 times the limit as x approaches 2 of x cubed minus 4 times the limit as x approaches 2 of x squared plus 2 times the limit as x approaches 2 of x minus the limit as x approaches 2 of 1. And now each of these guys' graphs, I do know. What's more, even if you didn't have the graph, you have the rule, those common limits, particularly this top one here. This guy, together with the rule that constants pop out, and you can split up over addition and subtraction, is enough to give you the limit of any polynomial. So this first piece, the limit as x approaches 2 of x cubed, well, that's like having c equals 2 and n equals 3 here. So that would be 2 cubed. In other words, you can just plug in the 2. So this will be this. Similarly, this piece will be this. This piece will be this. And then the limit of a constant function, remember, is always just that constant. So 3 times 2 cubed is 8. 8 times 3 is 24. Minus 2 squared is 4. 4 times 4 is 16. Plus 4 minus 1.
I have a question.
Sure.
So you don't do it for the last one, like the minus one, because it doesn't have like the exponent or the power.
Yeah, there's no x here, right?
Gotcha.
So this is the limit of a constant function. Imagine the graph y equals 1. That's a horizontal line, right? Going through the point 0, 1. Anywhere along that graph, no matter what the x value is, the y value is always 1. So if I let my x values get closer and closer to 2 along that graph, my y value will always be 1. And in general, the limit of a constant function is just that constant value. Yeah, fair question. So if we're comfy with that and each of these, then we get to here. And then we just need to perform the arithmetic. So 24 minus 16, that's 8, plus 4 is 12, minus 1 is 11. Limits of rational functions work similarly as long as the denominator is non-zero in the limit. So if I wanted to take the limit as x goes to negative of x squared plus, let's say, 5x plus 6 over x minus 3. If I wanted to take the limit of this thing, I can first use the rule that says you can split up over the fraction. So this would be the limit of the top. Divided by the limit of the bottom. And then I could go through this whole thing here where I split up the polynomial upstairs and pop out the constants. But we know what the net effect is going to be. This will be just plugging in -1 everywhere there's an x. The only thing we should check is that in this step where we split up the top over the bottom, that this piece isn't going to 0. Oh, well, as x gets close to -1, x minus 3 gets close to -4. So that's fine, that's not 0. So upstairs here we'll just have -1 squared plus 5 times -1 plus 6 divided by -1 minus 3, which is the -4 we mentioned a minute ago. And then that numerator, -1 squared is +1, plus 5 times -1, that's +1 minus 5, that's -4. -4 plus 6 is +2. And then downstairs here we have -1 minus 3, that's -4. So this is -1/2. So even though I have no idea what the graph of this function looks like, I can still calculate the limit essentially just by plugging in, as long as I'm sure the bottom isn't 0 or I'm not running into domain problems, that sort of thing. The fun begins when you do run into domain problems. Yeah, pretty much. Ali asks, so you're just plugging in, right? The answer there is yeah, pretty much. Like I said, the fun begins not here where you are essentially just plugging in. The fun begins when you do have a problem. Like what do you do if the bottom is 0? That becomes a totally different matter. Make sure we're not skipping over anything important. Yeah, so here's essentially what they're saying. If f is a polynomial or rational function, you can call this a theorem if you want. If f of x is a polynomial or rational function, and x equals c is in the domain of f of x, then the limit as x approaches c of f of x is just what you get by plugging in, right? That's a formal statement of the thing we just discovered. But again, the fun is, what do you do if this number is not in the domain? What do you do if you can't just plug in? What do you do if the bottom is 0 or you run into some other similar domain issue? In those cases, we need to get clever with our algebra, and this is kind of the first big hurdle. So yeah, this example, which we've dealt with before. You may remember this from last Wednesday. The limit as x approaches 1 of x squared minus 1 over x minus 1. So last time when we solved this limit, what we did is we graphed this function. We went through all the work that you would go through in a pre-calculus class to figure out what the graph of this function looks like. And then looking at the graph, we were able to say that this limit, I won't spoil it for you, but that this limit does exist and has a particular value. I can't just split this up. I cannot split this as the limit as x goes to 1 of x squared minus 1 over the limit as x goes to 1 of x minus 1 because the bottom is 0. So even though this is a rational function, the number that we're trying to approach isn't in the domain because it makes the denominator equal to 0. It also happens to make the numerator equal to 0. But remember, 0 over 0 is an indeterminate form. It's not equal to 1. But what we can do, and without looking at the graph, what we can do is algebra. The limit as x approaches 1 of x squared minus 1 over x minus 1, whatever else you want to say about it, it's definitely equal to the limit as x approaches 1 of x minus 1 times x plus 1 over x minus 1, because that's how the top factors. This function is literally equal to this function for all real numbers x. No, definitely no L'Hopital's rule. We don't have any idea what L'Hopital's rule is at this point because we don't have any idea what a derivative is at this point. L'Hopital's rule is much too big a hammer for this. Now, what is reasonable here is to take the factor of x minus 1 that you have downstairs and cancel it with the factor of x minus 1 that you have upstairs. Because remember, I'm not really interested in what happens at 1. I'm interested in what happens as I get closer and closer to 1. 1 does make the denominator equal to 0, does make this function undefined, but I'm not interested in what happens precisely at x equals 1. I'm interested in the pattern. As I get closer and closer and closer to x equaling 1, what are the y values of this function getting closer and closer and closer to? The factor that's causing the problem is the x minus 1 factor downstairs, because he's equal to 0 if you just try to plug in. But conveniently, there's also a factor of x minus 1 upstairs, and as long as x is not exactly equal to 1, you can cancel them. And so this limit is equal to this limit. And this guy is easy to work with. He doesn't have anything downstairs that could get upset with you. So you can just go ahead and plug in the x equals 1 here, and you get 2. So this is another example. We asked about examples last time where 0 over 0 or infinity over infinity come out to some value besides 1, 0, or infinity. Here's a case where something that definitely looks like 0 over 0, and it comes out to 2. And we could restructure so that it came out to any other real number that you wanted. But this is the general approach. This is the thing that you need to get good at for the first chunk of this class, is the algebra that will allow you to handle limits like this, where you can't just split up and plug in. There will be plenty of problems where you can just split up and plug in, just to remind you how it goes and what the rules are and to practice with the definitions. But the challenge, kind of the first, like I said, big hurdle in this class is getting your algebra skills sharp enough so that you can always find this common factor to cancel if you run into trouble like that, or whatever the equivalent issue is for the problem at hand. Questions on what we did here or why we did it? Okay, let's move forwards then, because we're getting close to being ready to start talking about the real good stuff. So this box statement is essentially saying what we just did. Let me come back here and be a little bit more explicit. So note, f of x equals x squared minus 1 over x minus 1 is equal to g of x equals x plus 1 for all x's except 1 itself. If you compare the graphs of these, here's the graph of f. Here's the graph of g. The only difference is f has a hole right here at 1. So at 1, 2. And that hole is what keeps us from being able to plug in right away. But that hole came from a common factor between the top and the bottom. When we cancel that common factor, we get a function that is slightly different, right? The domain of G is all real numbers. The domain of x plus 1 is all real numbers. What is true here is that this is equal to this except at 1. But because the limit doesn't care about what happens exactly at 1, it only cares about the pattern as you get closer and closer, you can take the limit of f by taking the limit of g. And remember, every time you cancel like this, what you're doing is you're like deleting a hole. So you are changing the function. So this really is a different function than this, hence the two different labels, g and f. They have different domains. But aside from that one tiny difference, they're identical. So the limit at 1 in particular of f is the same as the limit at 1 of g. They're both equal to 2. And you can take the limit here just by plugging in, even though you can't do that here. So that's the blue box statement there that we were just looking at in the textbook. The way it usually works out is you have to factor and cancel. Sometimes you'll have to combine some logarithms and cancel. Sometimes you'll have to do different bits of algebra, like multiply by a reciprocal and then cancel. But it always comes down to a certain amount of algebra, I don't want to call them tricks, but a certain amount of comfort with algebra about manipulation and then usually a cancellation somewhere. So we got to understand how cancellation works, why cancellation works, and what the result is. So here's the graph before the cancellation. Here's the graph after the cancellation. This guy is happy at 1. This guy is unhappy at 1. But aside from the behavior exactly at 1, these guys are identical. So you can take the limit here, and it will be the same as what you get if you took the limit here. But it's hard to take the limit here purely algebraically because the denominator is 0. Easy to take the limit here purely algebraically because there's no domain issues. You feel comfy with what we're saying there? Any questions about the concept being presented here? Okay. So you might be asking, why do we give a shit about this? Whoa, oh, sorry, my dot cam just decided to turn itself off. Might be asking, why do we care so much about this? The answer is the main object of study in the first half of this class, come on, goddammit, there we go, is what's called the derivative. And the derivative is defined, Jesus, this thing, by limits that look like these, where the denominator is 0, often the numerator is 0 as well, and you need to do some clever calculation to get where you want to be. There are some other examples here before we get to a derivative example. I suppose it couldn't hurt to look at this piecewise guy. Well, where did they do the split? At 1. So let g of x be x plus 1 if x is not equal to 1, and be equal to pi if x is equal to 1. Here you could make use of that theorem right away. So g of x is this guy everywhere except at 1. At 1 he's equal to this guy. We want to find the limit as x approaches 1 of g of x. Well, I know by the result we just discussed that if two functions are equal everywhere except at the point where you're trying to take the limit, you can go ahead and take the limit of the function that it's usually defined to be. Because remember, we're not considering x is exactly equal to 1. The only time g of x is equal to pi is if x is exactly equal to 1. Everywhere else, he's equal to x plus 1. So g of x is equal to x plus 1 everywhere except at 1, so the limits have to match. And then that limit, again, is 1 plus 1 is 2. Here the graph looks similar to the graph of the functions we were just playing with. I'll mark this as 1. X plus 1 then would look like this. And pi would be like up here. So this is the graph of g of x. And again, I don't care about what happens exactly at 1. I just care about what happens nearby. And if I was walking along this graph, getting closer and closer and closer to having x coordinate 1, my y coordinates would be getting closer and closer and closer to 2, even though the value of the function at 1 is way up there at pi. Okay, so these examples are cute. But like I said, the real reason we care about this stuff is because of the way the derivative is defined. So this next example is one that you're going to see various flavors of all the way up through exam 1. We usually use the symbol h for reasons that I'll explain when we get a little bit deeper into chapter 2. We can look at 3 plus h squared minus 9 over h. I run into the same problem here as I did in the x squared minus 1 over x minus 1 limit. If you try to plug in h equals 0, the top is going to be 3 squared minus 9, that's 9 minus 9, that's 0, and the bottom is definitely 0. So I can't just plug h equals 0. Because the object is undefined. When h equals 0. So instead, I'm going to have to do some amount of algebra. And here, there's only kind of one thing to even try. We should try foiling this out and just see what happens. If I FOIL out 3 plus h all squared, that's my firsts are 9. My inners and outers are both 3h, so 3h plus 3h will be 6h. And then I'll have my lasts plus h squared. And then I've got the minus 9 coming along from the problem. And then we're still dividing everything by h. The plus 9 here and the minus 9 there eat each other up. So I really have here the limit as h approaches 0 of 6h plus h squared over h. Now the factor that's causing the difficulty is the factor of h downstairs, and I do have a factor of h upstairs that I can bring out to cancel. So I'll factor an h from the numerator, and I'll be left with 6 plus h. Because if you were to redistribute this, this would be 6h and this would be h squared. And then I have the h downstairs, I can cancel those. So we get the limit as h goes to 0 of 6 plus h. And this line to this line is very much like this line to this line. Sure, g of x isn't always x plus 1. Those functions aren't exactly equal everywhere, but they are equal everywhere except at 1. So for the purposes of the limit, I can call them equal. Same here. This function isn't exactly equal to this function, but they are equal everywhere except where h is 0. Where h is 0, this guy is undefined, this guy's not undefined. And everywhere else, for every other h value, in particular for h values close to 0, these guys are equal. So the limits have to be equal, and that means I can plug in the h equals 0 here to get the value of this limit out. When I plug in 0 for h, 6 plus h is just 6. So this limit we began with, this is equal to 6. And if you've seen derivatives before, if this isn't your first run through calculus, or if you've looked this stuff up ahead of time, you might recognize this as being a difference quotient. This is like f of a plus h minus f of a all over h. It's a limit of a slope of secant lines. So what we're really getting out here is the slope of a tangent line. Now, to what function and at what point? Maybe, you know, I wouldn't expect you to be able to see that right away, but that is what we're talking about here.
Or couldn't you also separate it into limit 6h over h plus limit h base squared over h?
Let's see, you're talking about from here, right? Rather than factoring and canceling, split this
Yeah.
6h over h plus h squared over.
Bottom h goes
That would
towards
be
0,
okay,
so you
but then you would need to, so you could do that, but then in each of those expressions, you would need to then cancel an h. So it's a fair question. Let's take a look. What if we did this instead? That is kosher algebra. You can split fractions up across their numerator like that. But if I go to plug in h equals 0, I still have that problem in each of these expressions. So before we could actually get there, we would have to cancel the h and the h. We would have to cancel the square here with this h, and we'd get lim h to 0, 6 plus h again. So as long as at some point you cancel all the h's from the denominator or denominators, you'll be okay. The game is to get rid of the factors in the denominator that are going to 0.
I had a question.
Sure.
So with the function or the limit that we started with, and then the one that we ended with, and then you saying that they're equal to each other, aside from the fact that there is a there's a hole at h equals 0. Is there a way you can look at the function that we ended up with and know that there's a hole at 0?
No, when we cancel this, we're deleting the whole. That's
Okay.
what that does. So the cancel
So why
makes this end.
why do we do that? Wouldn't we want it the most exact answer, I guess?
I guess the question, so I see what you're saying, right? If we lose information when we cancel, why are we canceling, right? The only information that's lost is the value of the function at 0. So this guy doesn't exist at 0. He doesn't have a value at 0. There's a hole at 0. And what we're trying to figure out is what's the y value of that hole. That's what we're actually looking for here. When we use this limit, rather than plugging in, when we say I'm going to take the limit as h goes to 0, I'm asking, can you find for me the y value of the hole? We certainly can't find it by plugging 0 into this expression because we get something that's undefined if we do that. So we must go through this process in order to get the closest function to this guy, which is defined at 0. So this function not defined at 0, this function is defined at 0. So this is kind of the nicest similar function to the function we started with that is defined at 0. And we need something which is defined at 0 so we can use our limit laws and plug in. So our goal is to come up with this guy, come up with a function that agrees with my original function everywhere, but also has the feature that he's defined at 0. Does that answer your question?
Yes, thank you.
Okay, cool. Cool. All right, so we can play around with a few more of these. There are some other algebra tricks that I would like to show you. This is a good one. What was it? T to 0, t squared plus 9 minus 0 t squared. Yeah. So we have a similar problem here. If I try to plug in t equals 0, the top and the bottom are both 0. But here there's no obvious way to like factor or FOIL because of the square root. Remember, the square root of t squared plus 9 is definitely not t plus 3. Square roots do not play nice with addition or subtraction. Can't do that. So we got to come up with something else. I can't plug in. I can't like factor or distribute anything. But what I can do, if I'm hoping to get rid of this t squared downstairs, I could multiply top and bottom by the conjugate of this expression. So that's the algebra trick that we'll use. So conjugate, kind of like complex conjugate, if you've ever studied complex numbers. The conjugate of this numerator is the square root of t squared plus 9 plus 3. So I'll start just by writing everything down as it was, t squared plus 9 under the square root minus 3 over t squared. And then I'm going to multiply top and bottom by the conjugate of this expression, which is what you get just by taking this sign right here and flipping it from a minus to a plus. If this was a plus, I would flip it to a minus. So I'll have the square root of t squared plus 9 plus 3 over the square root of t squared plus 9 plus 3. I'm multiplying on the top and the bottom because I don't want to change the value of the function. This thing overall that I'm multiplying by here is equal to 1 because the top and bottom are the same. But then I'll distribute these pieces and these pieces, and we'll see what we'll get. Something nice will happen because I'm choosing the conjugate of that expression. When you FOIL out this big numerator, you'll get something nice. So remember that these fractions are grouping symbols. So when I multiply, I need to treat everything like it's in parens, like this. The square root of t squared plus 9 times the square root of t squared plus 9, those are my firsts. That's just t squared plus 9. Then my outers, that's 3 times the square root of t squared plus 9. My inners are minus 3 times the square root of t squared plus 9. And my lasts here are minus 9. So that's the numerator all FOILed out. And then downstairs, I'll just leave this as t squared times the square root of t squared plus 9 plus 3. Don't need to bother doing anything downstairs. The nice thing about this multiply by the conjugate trick is that your inners and your outers will always cancel. So you don't get any more square roots. All the square root stuff goes away. The blue box statements here add up to 0. I've got plus 3 apples and minus 3 apples. So this chunk here adds up to 0. So we'll have the limit as t goes to 0 of t squared plus 9 minus 9 over t squared times the square root of t squared plus 9 plus 3. And of course, now these 9s go. And you'll get lim t to 0, t squared over t squared times the square root of t squared plus 9 plus 3. So I'll give a second for you guys to sort out the algebra. Make sure you read carefully, make sure what you're writing down is correct. The nice thing about this multiply by the conjugate trick, again, is that the middle terms always cancel each other. So it's a good trick for getting rid of square roots. If you have a troublesome square root somewhere, like we did in this original problem, you can always multiply by the conjugate of that expression, and the square root, at least in the place it was, will go away. It'll introduce a square root downstairs, But that's actually not a problem here, because now that we get to this stage, I can cancel the t squareds. And you get limit as t goes to 0, 1 over the square root of t squared plus 9 plus 3. And because the conjugate has a plus here instead of a minus, this piece, this isn't going to go to 0. This is going to go to something else. This object is now defined at t equals 0, whereas the original was not. And I can just sub in 0 for t, and I get 1 over the square root of 0 squared plus 9 plus 3. 0 squared is 0. 0 plus 9 is 9. The square root of 9 is 3. So that's 1 over 3 plus 3, or 1/6. And I want to point out that this is not the same thing you would get if you tried to abuse the square root like that up there. Right? So you need this procedure. Okay, so let's start here. Any questions up to here? Are we all comfortable why this doesn't work? You can try plugging in some numbers. Plug in 1 for t. Over here you would have the square root of 10. Over here you would have 4. The square root of 10 is definitely not 4. So this definitely doesn't work. Okay, any questions through to this line? Feeling pretty good? All right. What about these last few steps? Any questions about how we canceled, what we canceled, where things went? Okay. Let's see if there's anything else more devilish that they can throw our way. These are not too bad. Some limits are best calculated by finding left and right hand limits separately. So we remember this, right? This is the definition of the limit existing. We had this last week. The limit as x approaches some number of f of x equals L. If and only if the one-sided limits match. This can be useful for piecewise defined functions like we've seen. Yeah, we can take a quick look at 7 and 8. So this is a lot of people either haven't seen or haven't really internalized the definition of the absolute value function as a piecewise function until they get to Calc 1. So let's take a second to do this. So I want to find the limit as x approaches 0 of the absolute value of x. And you might want to say, oh, well, I can just plug in 0 for x here, and the absolute value of 0 is 0. That's not entirely sound, because none of our limit laws tell us how to handle absolute values. The absolute value is a function that it's not a polynomial, it's not a power function, it's not exponential, it's not rational. It's not any of those things. So I can't jump straight to plugging in here. But what I can do is use the fact that the absolute value function is actually a piecewise function. Think about what absolute value does. If x is positive, if x is greater than or equal to 0, then the absolute value of x is just x. Like the absolute value of 5 is 5, the absolute value of 2 is 2. If x is negative, then the absolute value makes it positive. And the way you algebraically take a negative thing and make it positive is by slapping another negative on. So this is the piecewise definition of the absolute value function. And for a lot of calculus purposes, this is the best definition of the absolute value function. And then from here, you can calculate left and right limits separately. So the limit as x approaches 0 from the right of the absolute value function, absolute value x. Let's see, I'm taking the limit as x goes to 0 plus from the right. So I'm considering x's here which are just a little bit bigger than 0. In particular, they're positive. So I would use this top definition for this one-sided limit. And now that is a simple function, no absolute values. So I can just plug in. So the limit as x approaches 0 from the right of x, that's definitely just 0. And if I take the limit as x approaches 0 from the left of the absolute value of x, that means I'm considering x's which are just a little bit to the left of 0. In other words, I'm considering x's which are just a little bit negative. So I would be using this piece of my piecewise function. But negative x, just like positive x, goes to 0 as x goes to 0 because the negative of 0 is just 0. Therefore, since the left and right limits are both equal to 0, the overall limit exists and is equal to 0. This might seem a little bit boring until you think about the sort of stuff you can build up out of it. I'll say quickly here that this approach, this way of thinking about things, is very important when we start asking whether or not a function is differentiable, whether or not the derivative of a given function exists or doesn't exist. Not every function has a derivative. Some functions cannot be differentiated. And this sort of approach, where you take a left limit and right limit and check whether they match, it's not just important for what we're doing now, it's important for what we're going to be doing later with regard to derivatives also. So let's try a similar one. Let's find, if possible, the limit as x goes to 0 of the absolute value of x divided by x. I don't expect anybody to know what that graph looks like off the top of their heads. You could make a table if you wanted to and then try to sketch a graph from that. But we want to stay in the spirit of what we've been doing lately, where we're working algebraically. Since the absolute value of x is defined to be x if x is greater than or equal to 0, and the negative of x if x is less than 0, the absolute value of x over x, you can just divide each of those pieces by x. So it would be x over x if x is greater than 0, and negative x over x if x is less than 0. And I've pulled out the or equal to here because, of course, this thing is undefined at 0 because the bottom there would be 0. But no one would write x over x or negative x over x. They would cancel those to write them more nicely. X over x is 1. So this is equal to 1 if x is greater than 0. Negative x over x is negative 1. So this is negative 1 if x is less than 0. So again, we could take the one-sided approach. Remember, what we're trying to do is find the limit as x goes to 0 of this function, which we've now written nicely as a piecewise function in this way. So this implies that the limit as x approaches 0 from the left of absolute x over x. Again, I'm thinking of x's which are just a little bit to the left of 0. I'm thinking of x's which are slightly negative, so I'll be using this piece. And the limit as x approaches 0 from the left of the constant function -1, limit of a constant is always that constant. And the limit as x goes to 0 from the right, absolute x over x, is the limit as x goes to 0 from the right of, well, if I'm considering x is a little bit bigger than 0, I'm going to 0 from the right. This function, if I'm plugging in numbers that are a little bit bigger than 0, is equal to 1, because it's equal to 1 for all x's positive. So that's the same as taking the limit as x goes to 0 from the right of 1. But here you'll see the left and right limits do not match. So this implies that the limit as x approaches 0 of absolute value x over x does not exist. And the graph here, if you want to see it, looks like this. Right, so as we approach 0 from the left, we're staying down here at -1. As we approach 0 from the right, we're staying up here at +1. And there is no value that my y values from both sides are getting closer and closer to as we approach 0. So the limit at 0 overall here does not exist. Questions on this slightly more complicated absolute value problem? Okay. Let's see. There's this. All right, 140. So we go here at 12:30 to 1:45. We got a few more minutes. So let me see if there isn't something here I can do that'll be a little bit more exciting. These would follow from the same sort of stuff. The integer function we're not going to play with. Oh, the squeeze theorem. Yeah, this is important. So I'll finish with 2 theorems here, and then at the start of class on Wednesday, I will show you how to make use of them. Sorry. So this first guy just says if f of x is less than or equal to g of x for all x, or even just for all x near c, then the limits obey the same inequality. So if this function is bigger than this guy everywhere near c, then in the limit as x approaches c, this guy will be bigger than this guy. That makes sense, right? If the graph of g is everywhere above the graph of f, then in any limiting situation, the limit of g should be larger than the limit of f. This is kind of used together with compound inequalities to prove the squeeze theorem. In France, they call this the policeman theorem, and I always like that analogy. The cute story here is that if you're walking down the street and there's a policeman behind you and a policeman in front of you, and they're both going to the police station, you are also going to the police station. So if you're, I'll write it like this, if G1 is less than or equal to F is less than or equal to G2, so you've got 3 functions, your guy is in the middle of these 2 policemen, and the limits of the outer functions are equal to each other, say they're both equal to L, then the limit of the middle function must also be L. So G1 and G2 are your two policemen, and you are f of x. G1 is the policeman behind you. G2 is the policeman in front of you. If the first policeman and the second policeman are both going to the police station, your ass also going to the police station. And just like above here, this inequality needs to be true for all x near C. Usually in practice, the inequality will be true for all real numbers x, but it's not necessary that it be true for all real numbers x. There is a picture that goes well with this theorem, but it doesn't convey well on the dot cam because this thing doesn't pick up colors. I don't know if you guys can tell, this is actually a light purple that I'm writing in. I think it looks black on my screen. So I'll show you the picture as it exists in the textbook. Instead of using G1 and G2, they use F, G, and H. But you see here, the pink guy is the middle guy, the blue guy is the policeman behind you, and the green guy is the policeman ahead of you. If they're both going to the same value L as x approaches A, then the red guy, the pink guy, you, have to also be going to that value. So I've got 1 minute here to try and show you an example. If I wanted to find the limit as x goes to 0 of x squared times the sine of 1 over x, we know that the sine of 1 over x has lots of problems, right? As you approach 0, the sine of 1 over x does that crazy fast oscillation thing that we saw last week. But this x squared is somehow like tamping him down. I cannot do this by plugging in. Because the sine of 1 over 0 is not defined. Worse, in fact, the limit as x goes to 0, sine of 1 over x, forget the thing not even being defined, even the limit does not exist. So this piece on its own, the sine 1 over x piece, does not have a limit at 0, so you couldn't try to split this up over multiplication. And you can't just plug in because the function 1 over x is undefined at 0, so the sine of that is undefined at 0. But we can use the squeeze theorem. I need to build an inequality that looks like this and holds true for all x near 0. The neat observation is that the sine of anything, even the sine of 1 over x, is always bounded. It's always bigger than or equal to -1, and it's always smaller or equal to +1. This on its own won't get me the result, but if I multiply through by x squared, then I see -x squared is less than or equal to my function, x squared times the sine of 1 over x, is less than or equal to the positive x squared. So I started with an inequality that I knew was true based on the behavior of the sine function. The sine of anything, no matter what it is, it's always between -1 and 1. And then I multiplied through that inequality in each of the 3 spaces by x squared. X squared is a positive quantity, so you can multiply through an inequality without fear of messing things up. And now you can say the limit as x goes to 0 of -x squared, well, that's 0. The limit as x goes to 0 of positive x squared, that's also 0. Therefore, by this inequality, we'll call it star, and the squeeze theorem, the limit lim x to 0, x squared times the sine of 1 over x must be 0 also. So this theorem does two nice things for us. It gives you a way to find the value of the limit. It also guarantees that the limit exists because you're squeezed between two guys, both of whom have a limit at 0, and those limits match. So your limit must exist and match. Here's the policeman behind you. Here's the policeman in front of you. Both cops are going to 0. So you, stuck in the middle of those two cops, you have no choice but to go to 0 as well. The last thing I'd like to do with you here today is to take a quick look at the graph of this function compared to the graphs of these. So I'll pull up Desmos.
And then again, you could find out just thinking about it, because keep in mind that sine of 1 over x, we already said that it oscillates infinitely. Like at 0, it oscillates, when you take the limit, my bad. It just oscillates between 0 and 1. I mean, negative 1 and 1. And so if you multiply by 0, like, I mean, it just kind of makes sense if you...
I understand what you're saying, but the logic isn't quite sound because the limit of this guy on his own doesn't exist. So I could reconstruct.
But it oscillates between negative 1 and 1.
Right. Yeah, but it's possible that that oscillation behavior makes the overall limit fail to exist. Let me put it another way. If this wasn't an x squared, we would have a problem. Believe it or not.
So if it was just a regular x, we would also have a problem?
Right. Yeah, exactly. You need this thing to be going to 0 fast enough to overwhelm the oscillatory behavior. So you can have functions that are so janky, that oscillate so wildly, that even when you try to tamp them down, the limit still fails to exist. So you need to tamp them down hard enough. That's the idea. So here's x squared times the sine of 1 over x. Here's x squared itself, and here's negative x squared. So you see our guy, the red guy, trapped between the blue and the green. Even though he's oscillating, he's going to get smushed down hard enough that those oscillations can't fight. And he, even though he's undefined there, will still have a limit of 0. So the intuition you're describing is good. If you take something that's bounded and you multiply by something that goes to 0, you should get something that goes to 0, as long as the bounded function isn't so discontinuous that the overall limit doesn't have a chance of existing. So these are fun things to play with, and I'll give you lots of other examples that we can look at starting in class on Wednesday of this week. So I think this is a good place to leave it. If you haven't finished homework 1, please go ahead and submit an extension request. I'll be going through and granting those right now. And then I'll publish homework 2 here just as soon as I can. It might take me a few minutes. I've got one other class after this, but then you'll have homework 2 ready for you also. Any last minute questions before we sign out for the day?
Yeah. How do I check the attendance?
So you should go into your eSanta Fe, and I think maybe somebody else can help me out here because I don't see the student end of this. I think if you go to your schedule in eSanta Fe, you should be able to see whether you've been marked as attended or not. Is that correct?
Let me check.
Can anybody else here help us with that? Because I don't see.
Yeah, it's where you register for classes. Like you click my schedule after you log in. It's where whatever you register classes, just click my schedule where it says my classes. You should be.
Okay, so you go to the spot where you register
okay.
classes,
I see
click
it.
my schedule, and then look there. All right.
Yep. Okay, thank you.
If anybody has not been marked as attended but has been attending, of course, please let me know. Canvas message is the best way to do that. And we'll have all that stuff wrapped up. Just make sure you're working on the homework also, okay? Alrighty, guys, that's where I'm going to end the meeting for today. I will see everybody on Wednesday. Or if you want to come by office hours, I'll see you then. Take care.